So today we are. Fuck. What the hell? What subject is it again? Calculus? I'm really learning about the Newton's laws of relativity. Wait, that's the wrong subject. Fuck.
Oh boy, here we go.
Oh, yes, pie. I love me some good pie.
I think you're getting things mixed up. Are we talking about the Greek letter?
Of course, I mean the geek letter. I'm done with this. What if we make you symmetrical, slouve? I'm sorry? Hey, this is my project. The whole pie.
Who the hell are you? Where are you coming from?
Thin air. Anyway, the whole pie thing was my idea in the first place. This has some calculus. You can't kill me? Chill. You have some time to live. This helps show some calculus stuff. And particularly right now, we're doing symmetry.
This is what you get for being a bad calc teacher, by the way.
I'm not. Okay, so even functions. An even function is when the coefficient of the derivative is an even number. No. It's when f of negative x equals f of x. That means it's symmetrical across the y-axis. Like the axis powers? How? Actually, how?
Can we get back to our point?
No, I'm the teacher here. So, in the 18th century, there was this really smart guy. His name was Leonard Euler, and he made so many contributions to the sciences, especially mathematics. It's not what he's well known for, but he created the terms for even and odd functions. One moment. How the heck are you right?
I have the same question.
My dad insisted I get into STEM, so I majored in math history. Don't question it further. Anyway, also clarification. Euler didn't exactly invent these symmetries, but he did actually name them in Latin, not English, after certain things about parity. Pretty neat. Stop doing my job. So, Euler was pretty into sound and music and that kind of stuff. Can't blame him. Music's amazing. Anyway, this had to do a lot with sine waves, which are symmetrical. Only about certain lines. Yeah, that. So, when he was doing that, he remembered his ventures into parity and came up with a couple of useful and pretty complicated definitions for these functions. Well, complicated comparative definitions for even and odd numbers, at least. A lot of math is a lot more complicated.
An integer n is even if and only if there exists an integer k, such as n equals 2k, and basically just add or subtract a 1 from that for odd integers.
You're just being overly fancy. Anyway, Euler read stuff into calculus and noticed a few things that I don't quite remember. This disembodied voice will probably take care of that. After story time's over. Thank you. Anyway, before Euler was around, like long before, there were a bunch of Greek dudes. Euclid, Archimedes, and probably a few more. They were into shapes. In fact, Euclid invented the mathematical field of geometry. Well, Euclidean geometry at the very least. Euclidean geometry is an idea of the fractional symmetry, where you basically flip shapes across it like pancakes. I think. You're right, don't worry. Archimedes did a lot with three-dimensional shapes, and those have a lot of fractional symmetries too. There was also some stuff with Euclid called isometries, but I don't remember what those are.
Of course you don't.
Shut up! Anyway, I can see the look on that invisible being telling me that I should move on. So, and this is quite the logical jump, Euler took inspiration from Euclid's reflectional symmetry and the concepts that was bouncing around at the time called parity.
What a leap.
You're mean. I'm telling my dad to talk to your dad about this later. Be nice to each other. Anyway, as I said earlier, Euler's definitions of even and odd functions help him with the sound wave stuff. Sinusoids. Yeah, those. Anyway, Euler's concepts of even and odd symmetry helped in the work of people like Taylor and Fourier.
That second name sounds familiar.
Forfall is over there, just FYI. Also, Brooks Taylor is older than Euler. I also have no idea what you're on about with Taylor, but I guess if there's even functions in a series or something like that, that has a lot. That's also how Fourier series work. Well then, maybe Taylor's work helped Euler. Anyway, you're right about Fourier. Fourier series have a lot of wavy functions in them, all of which have to do with symmetry. Um, Let me take it from here. While Fourier series are important in a lot of mathematics, they aren't typically covered in any calculus courses. They appear to typically be covered in upper division math classes, but sometimes slightly earlier.
And how does a calculus I student know this?
If you keep shaking that law like that, it's going to cave in and you'll all die. Also, it's not that hard to look up. Just go on already. As I was saying, they're not in the scope of the course, but Fourier series appear to be able to be vastly simplified by the use of the implications of even and odd functions. After all, their main components are sine and cosines. This is all way too advanced for me to explain right it's now, though. If I looked at it for hours, I might be able to parse it, but I'm not doing that.
Yeah, you're writing a.
I'm not letting y'all die yet. Stop hitting that wall. Anyway, Fourier series are apparently useful, according to Wikipedia, for heat distributions. Why it is, ask a real mathematician. But if Fourier series are useful for heat distributions and symmetry is useful for Fourier series, I'd place some bets on symmetry being useful for heat distributions. If Slouve has nothing more to say, I'd like to get into more immediately useful math stuff. Nothing more. So, even functions, their when functions are symmetrical across the y-axis, and it just so happens that their derivatives are odd functions. F of negative x equals minus f of negative x makes an odd function. Well, you're not wrong, but that's just because that means f of x equals 0, and that actually is an odd function. It's also even though. Odd functions are when f of negative x equals negative f of x, and they're useful in interesting ways themselves.
What line are they symmetrical across?
Good question. I don't think there is a line. Kind of annoying, but I like to think of them as deriving into symmetry. Although not all functions that derive into symmetry are odd functions. All odd functions do, though. What symmetry does x to the 3.2 have? That's a question for sure. Let's do the math. So here you see if that we have x to the 3.2, and that's equals to x to the 16 fifths. X to the 16 has an even power, and is therefore evenly symmetrical. And the radical power 5 basically just makes the value smaller. What about x to the 3.14159? That or pi? Exactly, 3.14159. Okay, so x to the 314,159 has odd symmetry.
Is that where the names come from? Powers?
Something like that. Anyway, that has odd symmetry and it's to an even radical, so it's not symmetrical. There's no such thing as f of negative x in this case, unless you want to get into imaginary numbers. That's not in the scope of this class, though. And even then, no imaginary number is the equal or negative of a real. What about, in case you can't see the pattern already, be free to convert these decimal powers into radicals, and use the fact that x to an even power is even, and x to an odd power is odd, we can determine the symmetry of any power. For even functions, modifying them by any radical makes them still even. For odd functions, the radical must be odd, otherwise negative values of the odd function cannot be determined. What about decimal radicals? Just convert them into whole numbers. Anyway, let's go into what these mean for integration real quick. When a function is even on the closed interval from negative a to a, the integral of f of x from negative a to a is simply double that of the integral of f of x from 0 to a. This is because the areas under the curves are mirror images of each other. When it's odds, the integral of f of x from negative a to a is just 0. This is because as there's a mirror image of the part of with positive area that has negative area. Basically, it's all a matter of flipping part of the graph like a pancake and seeing how it lands.
Okay, is that all? I have a problem for you.
Yeah, I'm curious. What's this problem?
Cosmicron Incorporated is testing boats in a wave generator that makes a sinusoidal cycle of waves. The boats stay still on the x-axis, but bob up and down and rotate. They can withstand a rate of change of angle of 20 radians per second, or an angle of 100 degrees, whichever comes first, counterclockwise. The other way doesn't matter, because the water isn't slamming against the hull. However, the wave generator is angled at the maximum negative slope of the waves it makes. The beginning of the wave generator, when it's making a new wave, has the point of the wave with that slope, and then the exit point is at the wave's maximum point. Also, the wave generator is 100 meters long, and the waves it makes travel at speeds of 10 meters per second. We don't want to lose our boats, so we want to know beforehand how much they can deal with. What's the maximum slope the boat can withstand in this environment?
That's a tough one. I can see how it involves symmetry, but wow. So, you're basically saying we have a point with two variables, height and rotation.
Wait, that sounds similar to polar coordinates.
It's not polar coordinates, though. It's a Cartesian y value, and then there's some variable for rotation, say beta. There's still an x-axis, but the point doesn't move on it. The sine wave does, although it may be useful to consider it towards the change in x value of the point than of the wave.
Interesting.
The first things we need are variables to work with. So let's have these variables. Let A equal the x difference between the ends of the wave generator, and B the y difference of that. Also, S equals slope, T equals time, V equals speed equals 10 meters per second, and theta equals the angle of the boat. The theta dt is less than 20 per second. So much letting a 4-year-old could understand this. I don't think they could, actually. You get my point. Okay, so the general equation for typical sinusoids is the amplitude times the sine of the frequency times x. Converting this to our system, that would be w of x equals b over 2 sine of 1/4 a times x. That's x is going to be inside the sine, by the way.
You haven't accounted for the speed.
I'm about to get there. So, it alters the frequency? Yeah,
So we want to get the change in theta with respect to t somehow, right? Don't we want an equation for theta?
exactly. So, theta of t equals the arctangent of dy dt, since dy dt is the slope, and the arctangent of a slope is simply the angle creating that slope. So, y over t?
It's a derivative. Catch up.
What he said, but nicer in some way. And note that the maximum slope will be b over a, since the minimum is negative b over a, and this function is evenly symmetrical. The constant multiple and chain rules give dy dt equals 5b over 4a cosine of 5b over 2a. What? A little bit of simplifying too, just multiplying together. Anyway, we'll also use y prime for dy dt.
Can we please hurry this up?
The derivative of arctangent x is apparently 1 over 1 plus x squared, so using the chain rule, this makes dA dt equal 1 over, or 1 plus y prime squared, all of that times y prime prime. Doing even more fancy algebra and simple calculus, that's ended up being something that is a bit too long for me to want to say.
Mitä sä sanoit?
English.
I wasn't saying anything important.
So here we're doing a first derivative central on the function in dA dt. Finding a prime prime.
You're crazy.
I took my medication.
Siis mistä me puhutaan?
So anyway, a prime prime equals... Yeah, nope, not doing that. Anyway, from then, you'd want to find when a prime prime equals 0 or is undefined. Hopefully, since this is a sinusoidal function, it shouldn't be undefined. There's always going to be a rate at which the rate of change of the angle is changing. I should probably leave. Not happening. Anyway, these values produce maximums when a prime is positive. Those values are something involving some integer k, probably.
Huh?
I want to go home. Hopefully somebody on your team knows how to take derivatives. That's right, Cosmic Crown. I know who you are.
Whoa. How? I think you're getting things mixed up. Are you? Oh my. Okay. I'm sorry. Maybe we have the whole script for this. One more. You can work with that. You can. That's fine. No, 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 no. I, I have this. Oh my god. I have the. I'm about to. I have the same. Okay. 11th times the charm. Maybe one more. I have this. I have. I have. Why is this the hardest one? Get one of those. I don't care. So, how do I even say this? Okay. An integer is n. Wait, no, no, no. An integer n is even if and only if there exists an integer k, such as n equals 2k, and basically just add or subtract the. I was so close. I was so close. Maybe we'll skip that one for now. I'll do it with the big boy. um, and how does a calculus one student know this? Wait, is that an I? Hold on. Either one of those. I don't know. Is that an one or an I? What line are they? No, no. What line are they? Oh my god. What? 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 What line? It's hopeless. Um, what line are they? Use the first one. That was pretty good. Maybe a bit slow. Maybe a bit slower. Okay, is that all? No, no, no. Okay, is that all? I have a problem for you. No, 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 no. Maybe. One more. Okay, is that all? No, 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 no. That's not it. Um, that's gonna be another recording. No, coordinate. Hope. Wait, that sound. No, no, no. Wait, wait, wait. Something got in my throat. Hold on. So we wanna get. Hold on. We wanna get the change in theta with respect to season, right? Yeah. So we wanna get to the change in theta with respect to t. No, no, no. Let me try one more. I'll be more confident. So we wanna get in. Oh, no, no, no. So we wanna get to the change in my accent. So we wanna get to the change in say. Shit. It's- So we wanna get to the get get to two. Why can I not say two? Dos. So we wanna get to the change. Get to what is going on? So we wanna get to no. So we wanna get to the change in theta somehow. No, 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 no. So we wanna get to the get. I'm losing my mind. Hold on. Let me clear my throat. So we wanna get to the. I'm coming back to this one too. One more. It's a derivative. Oh, hold on. Derivative. Is that how you say it? Derivative. Oh my god, my tongue. It's a derivative. Catch up. That was maybe good. One more. Okay, how do I do this? No, no, no. I think it's gonna be a bit more fast. Um, I wasn't saying anything important. Okay, sure. Why not? Why not? See. I know. Let me try. Okay, I don't. Or like, hello, like, huh? Huh? Okay, last one. One more. Whoa, how do you do? No, no, no. Whoa, how do you do this so quickly? Okay, that wasn't good either. That wasn't good either. Whoa, okay. I gotta get this one right. I cannot. Why can I not say that? Whoa, whoa. How do you do this so quickly? You can use one of those. I don't care. I'm ending the recording. And now the three big ones. Okay, I've got this. I got this. An integer is n. No, no. Should I like an integer n is even if and only if there exists an integer. Okay, I'm gonna be failing at this for 15 minutes. Arrow subtract, and basically just arrow subtract. Why can I say subtract? Okay, and basically just basically just add or subtract, and basically just add or subtract a one from that for odd integers. I almost got it. And basically just add or subtract a one from that. Basically just add or subtract a one from that. Basically just add or subtract a one from that for odd. It worked. It worked. It worked. And basically just add or subtract a one from that for odd integers. I'm so good. Okay, let me try one more time, like the whole thing. An integer n is even if and only if there exists an. Oh my god, this is gonna take forever. An integer n is even if and only if there exists an integer k, such as n equals 2k, and basically just add or subtract a 1 from that for odd integers. I said I said odd like OTT. Okay, hold on. One more try, one more try. I think I got this. Just add or subtract the 1 from that for odd. I think one of those has to work, right? I'll do this one last. I don't even know how to start. So we want to get the change in theta with respect to t somehow, right? Don't we want an equation for theta? It's taking eons. My accent is too strong. You can ask me if like if one of these doesn't work and like I gotta revoice it. It's fine. Now I've got with, with this thing. Let me remove all distractions, each and every one, so that I only have this. Do I just go for it? Is that a sinusoidal? That's gotta be sinusoidal, right? Sinusoidal. Hold on. Let me. I'm gonna look at how to pronounce sinusoid. Okay. I've split it into like 10 parts, I guess, and I'm looking up how to pronounce sinusoidal. Why is Google lagging?
Sinusoidal.
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 Sinusoidal. Okay. We don't want to lose our boats, so we want to know before Europe. Okay, maybe one of those guys has to work, right? If it doesn't, tell me and I'll read some of these again, and we'll probably be fine. Good luck. You're gonna have to stitch this together.